algorithm. So a fundamental question in concentration of measure is, when is a function of independent random variables concentrating around its expectation? And this is the concentration of measure phenomenon. And it's, of course, very important in numerous applications in data science and signal processing and numerical linear algebra and so on. So one prototype example of a sort of general purpose concentration inequality tool for understanding, for showing this sort of result that's useful in lots of applications because it's very general, is Bernstein's inequality. And this concerns just sums of independent random variables. So random variables are independent, mean zero, and bounded uniformly. Then Bernstein's inequality gives this sharp estimate on the probability that the average of such random variables is sufficiently larger than its expectation. And we have, it crucially depends on a certain variance parameter, sigma squared, associated to the random variables. And the proof is almost one line, but not really, but just essentially it boils down to applying Markov's inequality on a properly transformed random variable and then optimizing for lambda. So the proof is not so difficult. So what we're interested in is extending these type of results from random variables to random matrices. I shouldn't say random matrices, I should say independent matrices, because I want to stress that I'm not talking about matrices where the entries of the matrix have a known distribution, which is sort of the more standard setting in random matrix theory, but rather just the matrix itself. The matrices are drawn as independent matrices. So for what functions do we have concentration of measure for independent matrix random variables? So following the Bernstein's inequality, we now in the past 10 or 15 years, it has been developed a matrix analog of that Bernstein's inequality. So we understand large deviations inequalities for sums of independent matrices. It looks a lot like the scalar case. We have n independent matrices. I'm assuming they're d by d here, but there's extensions to rectangular settings. Expectation, their expectation is a zero matrix, and bounded in the spectral norm. Then we can say that the spectral norm of the average of such random matrices, we can bound this. Why do we want to bound this? So many applications, again, in data science, covariance estimation, random graphs, sparsification, randomized linear algebra, and kernel methods and dimension reduction. It just shows up a lot. The proof is a little bit more complicated. Then you can't just extend the random variable setting straightforwardly, just because of intricacies that you encounter having to deal with matrices and the non-commutativity of matrices as opposed to random variables. And so the matrix Bernstein inequality, which is this large deviations inequality where we have the norm is the spectral norm. And the right-hand side looks almost the same as in the scalar case, just an extra factor of d, side dimension of the matrix. And this is an expression for sort of an important variance term that arises in the setting. And the proof is not too difficult. Once we use like the correct sort of results from Lieb on the convexity of a certain matrix, trace of a matrix exponential function. And then with that sort of one deep result in functional analysis, the result is not so difficult. And so we understand sums of independent matrices, or concentration of sums of independent matrices, and this sort of general Bernstein's inequality type setting. So we wanted to extend such a type of result from sums of matrices to products of independent matrices. Why products as opposed to sums? Products are almost as ubiquitous as matrix sums, and they're becoming sort of more and more at the forefront of the state-of-art algorithms in large-scale optimization, like reinforcement learning, game theory, and even in sort of more classical stochastic gradient descent type methods. Products of independent matrices and just products of matrices appear. Of course, neural networks too. I'm not going to tell you all the theory for neural networks here, but that's just like on a longer term horizon goal. Okay, so what can we say about products of independent matrices? So there's been a whole lot of work on products of random matrices and lots of really, really incredible work that I can't cover, but generally speaking, the previous results on products of random matrices have focused on either asymptotic settings where sort of the side dimensions of the matrices go to infinity asymptotically in a certain ratio, and then you get non-asymptotic results on the distribution of spectrum of the product and so on, and law of large numbers and central limit theorem types, which are not quantitative. And then on the other hand, results for products of random matrices that are non-asymptotic tend to mostly assume certain distributions of the random matrix element-wise, either say Gaussian matrices or non-negative entries or so on. And so I just don't want to take too long with this talk. I know it's the end of the conference, so I'll just use that as sort of a advertisement in case this looks interesting and you want to look at more details. But the kind of results we proved, here's one of the flavors of them, is more like a general purpose, assume not too much about the matrices and just give some concentration results for products in terms of the spectral norm of the expectation matrices and a certain proper analog of the matrix variance. So the variance of the matrices. And so this is just one. We have assumed that n independent matrices are d by d, but that's not so important as long as the dimensions are compatible. But let's just say d by d matrices, such that each matrix, the spectral norm of its expected matrix is smaller than mu. And for each matrix, the expected variance is less than sigma I times mu. Then the important variance quantity here is the sum of these sigma i's. And we can give these bounds on the growth of the product of n such matrices in terms of the growth of the spectral norm and the concentration of the matrix around its expected matrix and spectral norm. And I guess roughly speaking, what these type of bounds are saying is that if the fluctuations, the variances of the individual matrices, if the variance is small enough compared to the product of the norms of the expected matrices here. So as long as the product of the norms of the expectation matrices dominates the variance, and by dominates, I mean either in terms of going to zero faster than the variance goes up for contractions, products of contractions, or goes or stays bounded greater than one, but dominating the variance, then things work out. And I just want to mention pretty quickly that the proof of this type of result is not difficult once you use like the correct sort of deep result from functional analysis. Once you use the right result, then the proof is pretty easy. Let other people do the work for us. So we can talk about generalizing, even though we want to result in the spectral norm. Let's talk about other matrix norms that are easier to work with than the spectral norm, like Shatin norms for P finite. So Shatin norms are just, of course, P equals 2 is the Frobenius norm. That's the easiest matrix norm to work with. But for any Shatin norm with finite P, we can say something about the smoothness of such a norm in the sense of what's called two uniform smoothness of a matrix norm. And what this means is basically how close to being orthogonal is this matrix norm. So when P equals 2 and we have Frobenius norm, okay, well, we'll get to that in a minute. But anyway, So Ball, Carlin, and Lieb, again, Lieb's here in the 90s, proved this sharp constant on the smoothness of Shatin norms, that they have this, they obey this inequality with k equals p minus 1. And so a proposition that comes out of that is this sort of simple looking result that if we have a norm that's smooth, too uniform smooth, then the expectation of the norm of the sum of two matrices A plus B squared is less than or equal to the expectation of the norm of A squared plus K times expectation of the norm of B squared. And so now you see, like, when the two Shatin norm is the Frobenius norm has orthogonality. So for the Frobenius norm, this is an equality and K equals 1. And that's why the Frobenius norm is so nice, because it has this orthogonality, because in the expectation of B condition on A is 0. And so as we move away from the Frobenius norm for P greater, that we sort of still retain via the smoothness sum, not orthogonality, but bounded growth. And so this really plays nicely with matrix products, because we can rewrite the matrix product of n independent matrices as a martingale, going from the n minus first product to the nth product, and just decompose the product as the sum of two matrices, which satisfy exactly this form, the proposition. And so then recursively, we can get a bound on the Shatin norm of a product of matrices by just applying the smoothness proposition, and then applying our bounds in the theorem that we assume for the expectation of the norms of the expectations and the variances, and then recursively get a bound, and then get bounds on the Shatin norm, get a bound on the spectral norm using Markov's inequality. So that's sort of basically the proof. And so this is a sort of result. And now I can tell you about some applications where this type of concentration result is helpful. But first, I was going to ask if there are any questions. Okay, so then I'll go on. Okay, so some applications. The applications that I'm thinking about are in stochastic optimization. So probably everyone knows stochastic gradient descent, and in large scale machine learning, we often are wanting to minimize a loss function that has a finite, finite sum form, sum of component functions, fj. And so when n is very large, we can only use sort of first order methods that just evaluate gradients of the loss. So we have plane gradient descent with constant step size is a deterministic algorithm that converges smoothly like this. Stochastic gradient descent, where we draw, say, one component randomly from among these n components at each iteration, let's just say from the uniform distribution, and move in the direction of the stochastic gradient purple. It's a very randomized algorithm, lots of noise. So somewhere in between stochastic and batch gradient descent is mini-batch gradient descent, where one draws a b out of the little n component functions at each iteration and moves in the direction of the average of those component gradients. And this is sort of really just like a reduced variance stochastic gradient descent. And of course, the importance of doing a stochastic or mini batch compared to full gradient descent is that computationally you can just observe that you compute basically a factor of n divided by b number of gradients, component gradients for stochastic gradient descent, whereas batch gradient descent, you need to compute all n. So it's computation, so on. So that's the stochastic gradient descent. So one sort of, I guess by now, classical type of result on convergence rate of stochastic gradient descent. Sorry, this looks a little bit wonky, but anyway, this is a result from an older paper of mine with Deanna, Nutty Spraybro, but there are other results like this. Just sort of a nice situation is where you have stochastic gradient descent. You assume that the loss function f is mu strongly convex, and so it has a unique minimizer. this x star. You also suppose all of the n component functions are convex, not necessarily strongly, but convex and smooth, in which case there's a natural notion of condition number for the optimization problem. This is not the standard condition number, but this is, this is the natural condition number in the setting. And then stochastic gradient descent with constant step size with properly chosen step size will converge linearly to a sort of radius or region around the minimizing solution. And the radius of that region, depends on the amount of disagreement in the component functions in terms of the average squared norms at the minimizer x star. And we have an a linear convergence rate where the rate of convergence is like 1 over kappa, the condition number. So this is a stochastic gradient convergence result. In fact, so it's an exercise, I guess, that this convergence result can be derived just in terms of the matrix product concentration type of result that we showed. But we don't even need that concentration in the spectral norm to derive this result. We can use the same type of result with respect to the Frobenius norm instead of spectral norm. And then this result comes out maybe with a suboptimal constant C here on the noise. So I'm not going to claim it's exactly the right constant C there, but at least in the consistent case, it's the same. You get it. So you can just rewrite this as a product of independent matrices, because if you assume these components are smooth functions, then the mean value theorem says that the gradient, the difference in gradients of these functions is equal to the Hessian of the function at some point in between. That's the mean value theorem. And so that Hessian at that iteration is a random matrix. And so we basically are doing a product of identity minus step size times random Hessian matrix. So that's a product of independent matrices there. So one interesting thing about the operator perspective, or thinking about the trajectory of stochastic gradient descent, is just a matrix. It's just an operator, which is a product of independent matrices. That's an input-output map. Input to the output of stochastic gradient descent. It gives immediately, rather than just for a single trajectory analysis, like what you get for sort of for free, not just the expectation of the distance starting from one particular x naught, but really for any initialization x naught, because this perspective shows stochastic gradient is building up like a pseudo inverse, a random pseudo inverse to or operator. But anyway, so what I want to say here is, so did we really go overkill with trying to get matrix concentration results with respect to spectral norm? Because is Frobenius norm concentration enough for the interesting applications? Maybe we did go overkill asking for a spectral norm, but it turns out if we look at a more delicate variant of stochastic gradient descent, then spectral norm concentration does make a difference compared to Frobenius norm. So heavy ball momentum is a variant by Polyak of the standard gradient descent. So forget stochasticity now for a minute. Heavy ball momentum adds a second term to the gradient descent. And the limit collapses to a second order ODE in the continuum time limit. Heavy ball momentum theory, there's theory for quadratic objective functions. And for on quadratic, strongly convex quadratic objective function, this heavy ball momentum, where this additional term is a momentum term that sort of has the effect of making the trajectory converge more regularization. It's like regularization makes it sort of converge faster using the memory of which directions worked well in the past to sort of even out the trajectory compared to gradient descent without momentum. And so in the quadratic case, heavy ball momentum achieves a faster convergence rate. It has a linear rate of convergence, like 1 over square root of kappa, the condition number, whereas plane gradient descent has a convergence rate of 1 over kappa. And this 1 over square root kappa convergence is optimal. No algorithm, no first order algorithm in the standard setting of first order categorical setting can have a better convergence than that. So heavy ball momentum in practice, well, let me see. Okay, so the analysis for heavy ball momentum, even on just quadratics, it's more delicate than for stochastic gradient descent, because you have to, the analysis, you keep track of a transition matrix, and you have to keep track of the difference iteration k, the error at k+1 and error at iteration k at the same time, and write them in terms of the errors of the two previous iterations. And the transition matrix associated is not positive semi-definite, and it's not symmetric. So it has, with proper choice of alpha and beta, it has very good eigenvalues, which give this 1/square root of kappa, right? But it doesn't have small spectral norm. It doesn't have small any norm. The norm of this transition matrix is not less than 1, but the eigenvalues are. So one has to do a more careful analysis involving the spectral radius and of this operator in order to derive the convergence rate compared to plain stochastic gradient descent. Stochastic heavy ball momentum is very important in practice. Stochastic heavy ball momentum is a key component in state-of-the-art large-scale optimization algorithms that consistently beat other algorithms like ATOM. So stochastic heavy ball momentum, do the results of heavy ball momentum on quadratics extend to heavy ball momentum on quadratics in the stochastic setting? Theoretically, it is known that stochastic heavy ball momentum, when there's no mini batching, when the mini batch size is 1, cannot achieve acceleration compared to stochastic gradient descent. But if we look at just an illustration comparing gradient descent, this is just an illustration where gradient descent bounces back and forth and converges slowly. Heavy ball momentum converges quicker. We see that mini batch heavy ball momentum, if we just have the mini batch size large enough, when we do mini batch heavy ball momentum, it seems to retain the fast accelerated convergence rate of heavy ball momentum. And so the natural question is, it seems like a consistent hypothesis is that there might be a critical mini batch size B above which mini batch heavy ball momentum achieves the accelerated rate of deterministic heavy ball momentum. And that would explain why in practice, where mini batching is used in neural network training, it's helpful. And so what we could do is, by combining matrix Bernstein inequality for sums of independent matrices with the random matrix product concentration result to bound products of basically sums of matrices corresponding to mini batches, what we could prove with Tyler Chen and Raghu Oya Pragada at UT is that on convex, strongly convex quadratic loss functions, which for the moment, let's assume it's a consistent system. So A x star is equal to B. If we implement mini batch variant of heavy ball momentum, where we only draw a random batch of components instead of and compute the gradient in that batch rather than the entire gradient, and the batch size is above this threshold, which basically scales like the D times the smooth condition number of the problem, which is this, times square root the standard condition number of the operator A transpose A, then mini batch heavy ball momentum retains the same fast accelerated rate of convergence as heavy ball momentum, depending on 1/square root of kappa. We have a result also beyond the consistent setting, but some comments is in the inconsistent case, the mini batch heavy ball momentum, the result we get is, of course, it can only converge to a radius of the minimizer with the constant step sizes. The radius we get is probably not as good, it's not as good as other types of variants of plain stochastic gradient descent, like randomized Shatin Norms with averaging, of Mormon et al. in Indiana. So there's definitely room to improve on, I think, what we can say about the radius that this type of method can converge to. A couple weeks before our paper, the Paquettes and et al. Posted a really interesting paper, and they talked at this workshop about some work on stochastic heavy ball momentum. And they showed that in a setting, high dimensional setting with random quadratic, certain class of, with classes of random quadratic optimization problems, they have a tight bound showing a critical batch size of this size to get acceleration with heavy ball momentum. And so their batch size is kappa, the condition number, smaller than what we have. So there's a gap. So perhaps the result we have can be improved. The batch size can be made smaller by a factor of kappa, maybe. And just in terms of previous work, the only result I know about showing the fast convergence rate for stochastic heavy ball momentum is from Khan et al. In 2019, and they showed the accelerated rate under a bounded noise model, bounded variance model on the noise. But when we're talking about mini-batch noise that we deal with has an affine variance condition, because the noise variance will get larger if we're further away from the minimizer. So it scales with the norm of the batch gradient. And the random matrix product concentration, or the product concentration, really is very good with dealing with multiplicative noise like this, because the matrix product concentration is really about just getting this noise level small enough with mini batching so that in the matrix product concentration, the expectation term dominates the noise term, and it's a multiplicative thing there. So that's that. I feel like I've been talking a while. I guess I have 10 more minutes. Does anyone have any questions?
None right now.
Is it too slow? Is it boring? Should I stop?
Oh, I guess we have one.
When you're analyzing these optimization algorithms, where exactly does the matrix product come up?
Oh, that's a good question. So for this one, when you're looking at stochastic heavy ball momentum, then you're not applying this transition matrix at every iteration, because that would be deterministic. Instead, this A transpose A is like A just on the subset of rows corresponding to the mini batch you drew at that. So it'd be like A sub mini batch BK transpose A sub mini batch BK. So it's a random sketch, say a random sketch of the full matrix. And so that is a random sort of transition matrix. And you have a different random transition matrix at every iteration K. And so when you see, well, what is this after K iterations, you extend it out, and it's a product of K sort of random matrices. Each one is an expectation equal to this. Does that make sense?
Yeah.
Well, it's not exactly this. It's like identity. No, it is exactly this. Yeah, no, it's exactly this.
No more current questions, I guess.
Yeah. But so the stochastic gradient descent and heavy ball momentum, they have this, it's just a linear map from the previous error to the error at the next iteration. And so in the stochastic method, that linear relationship, it's actually a stochastic matrix, which varies from iteration to iteration. And so you naturally get a product of random matrices there. And so I don't want to go over too much technical stuff here, but another application where random matrix products come up, where we can use them to get new results that are interesting, is in streaming principal component analysis, which is a non-convex sort of optimization problem, but sort of one of the nicest non-convex optimization problems you can hope to have. So in streaming PCA, the setting is we have a stream of independent, or let's say IID matrices coming in, maybe one by one in time. And each one is in expectation equal to an underlying matrix M, which we're going to assume is symmetric. For PCA, it could be positive semi-definite, but really just needs to have real eigenvalues. The idea is that M is a matrix you want to compute its best rank K approximation to, but M is too big to store. M is giant. We don't even want to read in M in memory. So maybe we just draw a column or a rank 1 outer product formed by if M is positive semi-definite, and then that's our AT. And so we're just going to read in like column by column or batch of entries of M at a time, and try to collect them in a way to get an approximation of the best rank K subspace of M in streaming fashion. So let's just say what we want to compare a convergence rate to is an offline algorithm, where if we have M all at once, not M all at once, sorry, if we have these matrices all at once given to us, we would just compute the empirical average of the independent matrices, A bar, and then compute the best rank K approximation to A bar, and use that as approximation to the best rank K approximation of M. But as I was saying, there's interest in considering a streaming algorithm instead of an offline algorithm, where the model is that we only observe A1 at one point in time, and then A2, and then A3, and we can only keep, say, one average or one matrix of that size in memory. So what do we do? Well, one way to do streaming PCA is with what's called Oya's rule. It's an old algorithm proposed by Oya, and it looks like a randomized power method. It's start with a random guess of a D by K matrix. So think like a random K dimensional subspace, and then iteratively update that subspace by first sort of hitting the current AT that comes in at time T, hitting identity plus eta AT to the current guess of the subspace, and then orthogonalize, meaning do Gram-Schmidt to just replace this matrix with the matrix whose columns are orthogonal vectors, and do that for T iterations. And at the end, you have a subspace, and we want to ask how close is that subspace to the best rank K, the leading K-dimensional subspace of M. Now, why is this a product of independent matrices? This is a product of independent matrices, again, because this orthogonalization step, mathematically, we only have to do this at the very end of the algorithm. It's numerically, we do it at every iteration to keep the algorithm numerically stable so that things don't blow up. But mathematically, we can analyze this algorithm as just a product of identity plus eta AT's product applied to the initial. Okay, so Oya's algorithm is really just stochastic gradient descent again, projected stochastic gradient descent, because we can formulate an optimization problem of the best rank K approximation to a symmetric matrix M as finding the maximal orthogonal matrix Q, or matrix satisfying Q transpose Q equals identity, maximizing trace Q transpose MQ. And when we develop the stochastic gradient update, where the stochastic gradient corresponds to the sort of random matrix AT at time T, and then followed by a projection onto the manifold, which here is the manifold of matrices which are orthogonal. Then stochastic gradient update followed by projection back and forth gives us Oya's algorithm. So it's like projected stochastic gradient descent onto this Stiefel manifold. So what we can prove using the random matrix product concentration, caveat, there's a lot more complicated stuff we had to do besides random matrix concentration. So I'm lying a bit when I say it's just like, it's not a corollary of that. That is a component, but the hardest part is getting the initial part, phase one, because there's a lot of variance. But we could prove this result on after t iterations, how close the Oya subspace is to the best rank K subspace. This is a norm for some subspaces of dimension K, and we get a result that shows it matches the best offline convergence rate as if we had all the matrices at once and used just matrix Bernstein and random PCA up to a log factor. Now this result we have is comparing subspaces, so we need that the K and the K plus first eigenvalue of M really are distinct. Right. And then we have a dependence on that eigengap. So that's not great, but there's hope that there's a eigenfree analog of this, where we don't look for how close the subspaces are, but how close the objective function, the trace maximizations are. We haven't done that yet. But I just want to say, remark to put in context, before this result, there were results on the streaming PCA in two regimes where we're only doing rank K PCA. So we're just looking for the leading eigenvector, K equals 1, and that was Jane et al. They showed that for OHI's algorithm. And then another result of Alan Zhu and Lee in 17, they have basically this result only when the update matrices are rank 1. And so we can interpolate between those two previous results, and we interpolate because we use a spectral norm matrix concentration bound, and they implicitly used a Frobenius norm matrix concentration bound to get these end cases. I'm sorry, someone's talking. Is someone saying something?
Yeah, we had a question.
Oh, okay, sorry, I was just talking. What's the question? I'm pretty much done now.
I'll hand the mic off.
Hello, Rachel. What is V? Matrix V, what is that?
Oh yeah, yeah. So V, this is supposed to be V. See this? Doesn't this look like a V? Sorry, that's supposed to be a V. V is the underlying best k-dimensional subspace containing the leading K eigenvectors for the symmetric matrix M. So that's a ground truth. So this is gives a distance between the ground truth best k-dimensional subspace that we're trying to approximate, and QT is the subspace by OHI's algorithm after t iterations. So if QT equals V, then this is 0. And as QT is goes away from V, this gets larger. Okay.
Yeah.
So just in summary, we wanted to start, this is really just a work in progress. There are lots of extensions of these things. They're trying to figure out which matrix product theory is not too hard and which is too hard is part of the game. But we gave some sort of general purpose tools on giving concentration of norm growth and concentration for products of independent matrices. And I think they're a powerful tool for analyzing stochastic optimization algorithms beyond settings where people where they've been able to be analyzed without the matrix product concentration. And those usually involve settings where getting a Frobenius norm type of concentration is not enough. So for like heavy ball momentum, which is a very kind of delicate analysis with matrices where norms aren't really, you have to go beyond norms to eigenvalues, they're helpful. And on non-convex stochastic optimization problems like PCA, they're helpful. And there are other non-convex optimization problems like phase retrieval and so on, where we can try to slowly generally see how far can we go with this before the non-convex problems get too hard. Just probably the most biggest open question is, do we need independence? Deanna, I'm really just asking this question because I was hoping you'd be here to go from independent matrix factors to Markovian matrix factors, because that's going to be a lot more realistic in lots of applications where you don't have products of independent matrices, but you have a product of random matrices where the matrix at the tth iteration is random, but depends on the matrix at iteration t-1. This would be more realistic in like going to analyzing neural networks and beyond the NTK regime, beyond the regime where you just show that a neural network at the beginning, the matrix, the weights is well conditioned, and then you assume it doesn't move too much. That's the neural tangent kernel regime. So going beyond that, I think you need beyond independence matrix products, and also for doing adaptive gradient methods. And these are some references, and thanks.